Good morning everyone. I Vanshaj from BSc Chemistry Honours 3rd year. In this session of audio lecture for visually impaired student, I have prepared a audio lecture on chemical bonding covalent bond, which was taken from the book Modern Approach to Inorganic Chemistry, which was written by Dr. S.P. Johar. So let's start chemical bonding 1 covalent bond. A covalent bond is formed by mutual sharing of electron between the combining atom of the same or different elements. The atoms involved in the formation of a covalent bond constitute equal number of electrons for sharing in order to acquire configuration of nearest noble gas. The pair of electrons which constitute the bond between atoms is called a bonding pair of electrons. If there is one bonding pair of electrons between the atoms, the bond formed is called single covalent bond. On the other hand, two or three pair of electrons between two atoms constitute a double or triple bond respectively. According to Lewis's concept, the covalency of an element is the number of electrons which its atom contribute for sharing while forming a covalent bond. For example, the covalencies of hydrogen, oxygen and nitrogen are 1, 2 and 3 respectively. H ratio H or H minus H covalency equal to 1. O ratio O equals to O covalency equal to 2. N triple bond N covalency equal to 3. Now, theoretical treatment of covalent bond. The simple picture of covalent bond does not tell us anything about many interesting questions, such as arrangement of electrons in molecules, the shape of molecular orbitals, energy levels in molecules, etc. Like atom, we can write the Schrödinger wave equation for describing the behavior of electrons in molecules. However, it is very difficult to solve the Schrödinger wave equation for molecules. The solution can only be obtained by using certain approximations. There are two main approaches which are commonly used. These are valence bond theory, molecular orbital theory. Both these methods are based on the variation principle or method. Now, variation principle. It is a mathematical technique to calculate the lowest energy state or also known as ground state of the system. The basic idea of variation principle is that if psi 0 is the wave function for the ground state, then the energy corresponding to this wave function E naught is always less than associated with any other wave function that might be proposed. In other words, no proposed or trial wave function can have energy less than the true energy of the system. This method is illustrated below. The energy of a system can be calculated from the equation E equals to integrating psi star h psi d tau by integrating psi star psi d tau, where psi equals to wave function, psi star equals to complex conjugate of wave function psi, h equals to Hamiltonian operator, and d tau represent the volume over which integral is carried out. This relation can be used to calculate the energy of the system by knowing the value of psi. Now suppose we guess a particular wave function psi1 which may not be correct wave function. Then the corresponding energy say E1 can be calculated by using the above equation 1. Now let us guess some another wave function psi2 which gives energy E2. Then according to the variation principle, the calculated energy E1 and E2 are always greater than the true ground state energy E0. Moreover, the wave function which gives the lower energy state or closer to ground state is better approximation. For example, E2 is less than E1, then E1 is better approximation to energy and psi2 is better approximation to the wave function. Now suppose we guess a large number of wave functions and calculating their corresponding energy. The wave function which gives the lowest energy is the best approximation. Now valence bond theory. The valence bond theory was put forward by W. Hitler and F. London in 1927. It was later improved by extended by L. Pauling and J. C. Slater in 1931. The basic assumptions of this theory are: first, atoms do not lose their identity even after the formation of the molecule. Second, the bond is formed due to the interaction of only the valence electron as the two atoms come close to each other. The inner electron do not participate in the bond formation. Third, during the formation of bond, only the valence electrons from each bonded atom lose their identity. The other electron remains unaffected. The stability of the bond is accounted by the fact that the formation of bond is accompanied by release of energy. The molecule has minimum energy at a certain distance between the atom known as internuclear distance. Large the decrease in energy, stronger will the bond formed. The valence bond theory is based on two theorems. These are: if psi A and psi B are the wave function for any two isolated independent atom A and B with energy Ea and Eb respectively, then the total wave function psi for a system of two atoms will be given as the product of these two wave functions, that is psi equal to psi A into psi B. The energy of the system is given by E equals to Ea and Eb. Second, if there are several wave functions psi 1, psi 2, psi 3 and psi up to psi n for the same system, then the true wave function psi is obtained by combining the several wave functions linearly. Psi equals to C1 psi 1, C2 psi 2, C3 psi 3 up to Cn psi n, where C1 and C2 and C3 and up to Cn are the various coefficients indicating the contribution of each wave function. The square of these coefficients may be taken as the measure of the weights of the each wave function. These coefficients are so adjusted as to give a state of lowest energy, that is, a state of maximum stability. Valence bond theory formation of hydrogen molecules. Considering two hydrogen atoms Ha and Hb, when the two atoms are far apart from each other so that there is no intersection between them, the wave function of the system may be written as psi equals to psi A into psi B, where psi A is the wave function of Ha and psi B is the wave function of Hb atom. When we bring two atoms close together to form a covalent bond between them, then there will be interaction between them. The various interaction, that is the attractive interaction between nucleus of one and electron of second, and the repulsive interaction between the nuclei and the electrons are shown in figure 1. This system may be represented as Ha1 2Hb, where 1 represents the electron associated with Ha and 2 represent the electron associated with Hb. The combined wave function psi may be written as psi equals to psi A1 into psi B into 2, where psi A1 and psi B2 are the wave function for the separated atoms A and B respectively. Using this wave equation, we can calculate the energy of S2 molecule as a function of internuclear distance r. These energy changes are shown by curve 1 in figure 2. It may be noted that the energy of the two isolated hydrogen atom is conventionally taken as 0. It is clear from the curve 1, when the two atoms approaches each other, the energy of the system starts decreasing till a certain minimum value is reached. This stage corresponds to the formation of H2 molecule. The fall of potential energy is called bond energy. The bond energy comes out to be 24 kJ per mole. The experimental bond energy for the formation of H2 molecule has been found to be 458 per mole. This has been shown in figure 2 by dotted lines. Comparison of bond energy gives by curve 1 and experimental bond energy shows very poor agreement. Moreover, the minimum is found at a nuclear distance of about 0.90 angstrom, whereas the experimental bond distance in hydrogen molecule is 0.74 angstrom. Evidently, the wave function psi as calculated from equation 3 is not correct. This means that some interaction between the two hydrogen atoms have been ignored. The wave function was further improved to get the bond energy value comparable with the experimental value. Improvements. Some of the improvements are discussed as below. exchange of electrons, screening effect of electron, ionic character of H bond. First improvement, exchange of electrons. As discussed above, the equation 3 has been obtained on the assumption that the electron of two hydrogen atoms could be distinguished from each other. Therefore, the electron around nucleus A was labeled as 1 and the around nucleus B was labeled as 2. This assumption, however, is not correct. When a molecule is formed, it is not justified in labeling the electron because the two atomic orbitals overlap and the two electrons become indistinguishable from each other. We can no longer be sure that electron 1 will always be near the nucleus A and electron 2 will always be near the nucleus B. In other words, the state in which the electron 1 is near nucleus Hb and the electron is near Ha is equally probable. In other words, the state in which the electron 1 is near nucleus Hb and the electron 2 is near nucleus Ha is equally probable. Therefore, the system of two hydrogen atoms may then be represented by two different states, first and second, as shown below. In state 1, nucleus A is associated with electron 1 and nucleus B is associated with electron 2. In state 2, nucleus A is associated with electron 2 and the nucleus B is associated with electron 1. If psi 1 and psi 2 are the wave function associated with state 1 and 2 second respectively, then these may be written as psi 1 equal to psi A into 1, psi B into 2 and psi second is equal to psi A into 2, psi B 1. Now, if the system can be represented by the wave function psi 1 and psi second, then the true wave function is the linear combination of these wave function, theorem 2. Thus, psi equals to c1 psi 1 plus c2 psi 2, where c1 and c2 are the coefficient which gives the contribution of the wave function 1 and second respectively to the total wave function psi. In case of hydrogen molecule, the two wave functions are equally probable and therefore they must contribute with equal weight. As discussed earlier, theorem 2, the weight of each wave function is proportionally to the square of its coefficient, so that weight of wave function equals to weight of wave function second, c1 equals to plus minus c2. Thus substituting the values of c1 and c2 in equation number 5 as c1 1, c2 equal to 1, c1 equal to 1, c2 is equal to minus 1, we get two equations. The wave function psi positive is called symmetric combination and the wave function psi negative is called antisymmetric combination. Thus, calculation of energy associated with these wave functions psi positive and psi negative as a function of internuclear distance is represented by curve second and third respectively. Inspection of figure 2 shows that energy curve second corresponding to wave function psi positive has significant lowering in energy. The bonding is possible in this state. We may therefore regard psi positive as a bonding state. The bond energy corresponding to this wave function is 303 kJ per mole and the internuclear distance is 0.80 angstrom. This value of bond energy is better than calculated from the wave function corresponding to equation 3, that is 24 kJ per mole. Thus, the wave function has been improved if the electron on the atoms are exchanged. The additional lowering in energy for a molecule obtained as a result of concept of exchange of electrons between hydrogen atoms is called the exchange energy. On the other hand, the plot of energy of the system using the wave function psi negative shows increase of energy as the two atoms approach each other. This represents repulsive or non-bonding state. Thus, bonding is not possible in antisymmetric combination. Thus, the symmetric combination of atoms result into bonding between the atoms, whereas antisymmetric combination leads to non-bonding. Moreover, symmetric combination gives bond energy, which is a good improvement over curve 1. The wave function psi positive equation 6 is also referred to as covalent wave function. Therefore, it may be written as psi-covalent. The reason is that in state 1 as well as state 2, one electron is associated with one nucleus and the other electron is associated with the other nucleus. There is no charge separation. Now, second improvement, screening effect of electrons. The wave function given by equation 6 is further improved by considering the screening effect of the electrons. When the two atoms come close to each other, the electron of one atom shields the electron of other atom from the nucleus so that the electron do not feel the full charge of the nucleus. The actual charge felt by an electron is termed as its effective nuclear charge. This will be evidently less than the actual nuclear charge. Now, if we use the value of effective nuclear charge Z effective instead of actual nuclear charge and improve the wave function given by equation 6, bonding energy of 365 kJ per mole is obtained. This is shown by the curve 4th. Third improvement, ionic character of HH bond. The bond energy of 365 kJ per mole is still appreciably smaller than the experimental value of 458 kJ per mole. This shows that psi positive still does not give the true orbital wave function for H2. Evidently, further improvement of orbital wave function is needed. In the first improvement, we have allowed the electrons to exchange, but we have restricted the electron must exchange simultaneously. This corresponds to the covalent character and therefore psi positive is also written as psi covalent as psi covalent equals to psi A1, psi B2 plus psi A2 and psi B1. However, it is quite possible that both the electron may simultaneously be present close to one nucleus or the other. This means that both the electrons 1 and 2 either represent on HA or on atom HB, resulting in ionic character of bonding. These states may be represented by structure 3rd and 4th as given head. Resonance and resonation energy. The valence bond theory results into concept of resonance. According to valence bond theory, a molecule of hydrogen atom cannot be represented by a single structure, which could account for the stability of the molecule. In effect, a molecule of hydrogen may be described by the following structure, which have ionic as well as covalent character. As has been discussed earlier, the actual wave function and the stability of the molecule is obtained by suitable combination of wave function of these three structures, but can be represented by combination of these. The contribution of each structure can be determined by its nature and stability. The actual structure of the molecule is considered as resonance hybrid of these structures. The phenomenon is called resonance and the indivisible structure are called resonating structure or canonical structure. These resonating structures are drawn with double head arrows between them. It may be noted that none of the resonating structure have real existence. Also, it does not mean that the actual molecule exists for a certain fraction of time in one form and for fraction of time in another form. In fact, the actual structure has no pictorial representation. The resonating structure are only a convenient way of picturing molecules to account for all the properties of a molecule. The resonance hybrid may be compared with a mule. For example, like resonance hybrid, a mule has a characteristic of a donkey and the horse, but at no time it is either of these. Thus, resonance may be summarized as follows. When a molecule cannot be completely represented by a single structure, but its characteristics properties can be described by two or different structures, then the true structure is said to be resonance hybrid of these structures. The phenomenon is called resonance. For example, hydrogen molecule is considered to be a resonance hybrid of above three structure marked 1, 2 and 3rd. These may be represented as the molecule is said to be resonate between the three resonance structure. Resonance energy. As mentioned above, the resonance hybrid is more stable than of the contributing structure. The extra stability of the resonance hybrid as compared to the more stable of the various resonating structure is called resonance energy. Resonance energy is thus defined as the difference between the actual bond energy of the molecule and that of the most stable of the resonating structure. Resonance energy is equal to actual bond energy minus energy of most stable of resonating structure. For example, thus resonance energy of carbon dioxide is 138 kJ per mole. This means that the actual molecule of CO2 is about 138 kJ more stable than the most stable structure among the contributing structure. This can be easily illustrated as given below. Suppose E1, E2 and E3 are the energy of three resonating structure of a molecule. Their energy are shown in figure number 3. It is evident that among these E3 has the lowest energy, most stable contributing structure. If E0 is the actual energy of the molecules experimentally determined, then resonance energy is E3 minus E0. Rule for writing resonating structure. To explain the characteristic of a molecule, a number of resonating structures may be written. The energy of different resonating structures should be as close to actual molecule as possible so that the structure have significant contribution. There are certain rules which permit the selection of the structure which contribute towards resonance. The following are the essential rules for writing resonating structure. The contributing structure should have the same atomic position. They should differ only in position of electron. For example, the following two structures of the phosphoric acid are not resonance structure because they have different position of atom in two structures. The contributing structure should have the same number of unpaired electrons. For example, the following three structures may be written for nitric oxide NO. In these structures, structure 3rd is less important than the 2 structure because it has 3 unpaired electrons, whereas structure 1 and 2nd have only 1 unpaired electron. Similarly, we have written 3 structure for benzene C6H6 as. Obviously, in this case, structure 3rd is unstable because it contains unpaired electrons. Experimentally, it has been observed that benzene does not contain any unpaired electron. The contributing structure should not differ much in energy. This can be explained by taking the example of benzene. For benzene, 5 resonating structure may be written as the structure 1 and 2nd are due to calcules and are called calcule structure, and structure 3rd and 4th and 5th are due to Diwar and are called Diwar structure. The Diwar structures are less stable and therefore more energetic than the calcule structure. This is on account of the long bonds across the ring. It looks highly probable where therefore that the only calculus structure 1st and 2nd are real contributing structure. Thus benzene is mainly the resonance hybrid of structure 1 and 3rd written as. 4th one, contributing structure should be so written that the negatively charged resides on an electronegative element and positive charge resides on an electropositive element. For example, the three possible structure of HCl are structure 3rd in which the negative charge resides on an electropositive element H and positive charge resides on an electronegative element Cl is ruled out. HCl is therefore a resonance hybrid of two structure 1 and 2nd. 5th point, in contributing structure like charge should not reside on adjacent atom. This means that contributing structure should be so written that unlike charges reside on neighboring atoms, while like charges are separated as far as possible. For example, resonating structure of nitrous oxide N2O may be written as follows. In this case, structure third is not feasible because it places a positive charge on the electronegative oxygen atom and also has positive charge on the adjacent nitrogen and oxygen atom. Similarly, for hydrozoic acid, the following three structure may be written as. In this case, the structure third is insignificant because of positive charge on adjacent atom. Sixth point, the greater the number of covalent bonds, the greater is the contribution of the resonating structures. Thus, the doubly bonded structure second, third and fourth of BF3 molecules shown below are more important because of the formation of an additional covalent bond. Resonance structure of some molecule, hydrogen molecule S2. The various resonating structure of hydrogen molecule as discussed above are. Second, oxygen molecule. The bonding in O2 molecule is generally represented as. According to this structure, there is a double bond between two atoms. Each atom has two unshared pair of electrons. However, in addition to these covalent structure, two ionic structure may be written as. This is all from my side. Thank you and have a nice day.